Okay, this is lecture number 15. Let us do equation of plane, equation of line, distance of a point from plane, etc. in three-dimensional coordinate geometry. So the first exercise that we are going to do is equation of plane passing through 3 points: P1 x1 y1 z1, P2 x2 y2 z2, and P3 x3 y3 z3. In vectors, already we have found out this. Suppose P is any point in the required plane. So P is any point, this is say P1, P2, P3, and P is any point in the plane. Then this vector PP1 should be coplanar or a linear combination of P2 P1 and P3 P1, or now using scalar triple product, a box product, the volume of these three vectors, box formed by these three vectors as a coterminal edges should be 0. So P1 dot P2 P1 cross P2 P3 P1 should be equal to 0. That is what is the condition, and we know that this is equivalent to writing the determinant PP1 is x minus x1, y minus y1, z minus z1. P2 P1 is x1 minus x2, y1 minus y2, z1 minus z2, and this is x1 minus x3, y1 minus y3, z1 minus z3 is equal to 0. So this should be the equation of a plane passing through 3 points. We should leave it at this stage. If required, we can do the calculations when it comes to numerical calculations and get the equation of plane. Now, what will be the change in this? Question number 2. Equation of plane passing through P1, x1, y1, z1 and parallel to the lines whose direction ratios are L1 M1 N1 and L2 M2 N2. So the only these two rows are going to change. The answer for second is going to be equal to x minus x1, y minus y1, z minus z1, L1 M1 N1, L2 M2 N2. This 3 by 3 determinant box product should be equal to 0. This is what is going to be the answer for second. So if you have been given a point and given the direction ratios of the two lines, then this is what is going to be equation of plane. Now let us find out equation of line passing through a point whose direction ratios are P, Q and R. This is going to be important. You will require to use this many times, many times. So now I forget to tell you that you should try to develop these equations on your own, but I am sure you must be pausing this video, trying to do yourself. If you are successful in doing that, nothing like it. If not, then you have to go through the video and look at the proof or answer. Now, equation of line passing through P1 having direction ratio. So we remember R is equal to A plus T times B was our equation of line. Now it is passing through A and is parallel to B. That is what our understanding was. So in relation to this, our A is going to be equal to x1i plus y1j plus z1k. This is what is going to be our A, and what will be our B? B is going to be pi, these are direction ratios, so P times I plus Q times J plus R times K. This is what is going to be our vector B. And what will be R? R will be equal to x times I plus y times j plus z times k. So if we substitute everything over here, the xi plus yj plus zk is equal to x1I plus y1j plus z1k plus t times pi plus qj plus rk. This will be our equation of line. However, now if we compare the coefficients, we get x is equal to x1 plus p times t, or maybe t times p. y1 is equal to y1 plus t times q, and z is equal to z1 plus t times r. Now this is what is the equation of line. We have to specify the equation of line in three-dimensional space parametrically. That is what is this parameter. Yet another way of expressing this equation. So this is one way of expressing equation of line. We call this also an equation of line. Base point is x1, y1, 0, and direction through which it is going is p, q and r. However, if we just separate this t, parameter t, then we get x minus x1 upon p is equal to y minus y1 upon q is equal to z minus z1 upon r, which is equal to t. This is the standard form, or this is how equation of line in three-dimensional space is written. Now let us understand this. What do we mean by x1, y1, z1? The line is passing through that point. We may call that point as base point. So x1, y1, z1 will definitely satisfy this equation of line by putting x is equal to x1, y is equal to y1, z is equal to z1. We get 0 is equal to 0 is equal to 0, and in that case the parameter t is also 0. If we put t is equal to 0 in this version, then we get x is equal to x1, y is equal to y1, z is equal to z1, everything tally. Now we are putting these PQRs in the denominator. It is actually for the convenience. It might happen that one of PQR could be 0, two of them could be 0 if the lines are parallel to XY plane. If the lines are parallel to some axis, then one of the values could be 0, and in that case we will have to write it maybe in this form. It will be safe to write because it is in multiplication. But we need to understand, if I am not writing z in this form, that means r is going to be 0 or something like that. But this is the standard way of expressing straight line in three-dimensional geometry. We need to understand. Now, what are these denominators? They are the direction ratios of the line. So, what is the vector to which the line is parallel? It is, you have to look at the denominator. Pi plus qj plus rk is the vector to which this line is going to be parallel. The way I have said, ax plus by plus cz plus d is equal to 0. Those a, b and c's are the direction ratios of the vector which is perpendicular to the plane that we are talking about. p, q, r, the denominators here are the vectors, the direction ratios of the vector which is parallel, which is in line with the required line. So we are done with the equation of straight line. Now normally in the class we take some numerical problems so that we use these equations. However, right now in video we are not going to take those numerical problems. Let us finish the theory requirements. So the next in the pipeline is how, if suppose two lines are given to you, how do we check whether they are coplanar lines or not? Okay, so let me write down two lines quickly. X minus x1 upon Lp upon L1 is equal to y minus y1 upon m1 is equal to z minus z1 upon n1. This is one line, and second, x minus x1 upon L2. It need not be x1, it should be some other point, is equal to x minus is equal to y minus y2 upon m2 is equal to z minus z2 upon n2. Suppose these two lines are given to us and we want to check whether these two lines are coplanar or not. Then suppose point A in this case is x1i plus y1j plus z1k. Point B here is point B, or maybe we had referred to this point as C, which is x2i plus y2j plus z2k. What is the direction vector B here is L1i plus M1j plus N1k. What is the direction vector D here is L2i plus M2j plus N2k. And therefore what is the equation of line? This line R is equal to A plus T times B, and R is equal to C plus some Q times, Q is already written somewhere, no, Q times D. Okay, so these are the two lines that we have. And then the condition for our coplanarity of the two lines were, if you take box product of B cross D, I mean B cross D with A minus C. So A minus C dot B cross D, if it was 0, that means box of ABD is equal to box of CBD. That means these two lines are coplanar, which we have done in few lectures before. So if we want to exploit this condition, then what do we write? It is going to be corresponding 3D equation will be x1 minus x2, y1 minus y2, z1 minus z2. B is L1, M1, N1, and L2, M2, N2. This is supposed to be equal to 0. So if this happens, then the two lines are coplanar. Now here, suppose the lines are given in this form and you are comfortable in dealing with this, then you need not remember this, you will automatically get it, right? Now suppose if we want to find out equation, now these two lines are coplanar, they satisfy this condition, we want to find out equation of that plane, then you should either replace A by C or A by R or C by R. That will be the equation of plane. Equation of plane therefore would look like R minus x2, x minus x2, y minus y2, z minus z2, L1 M1 N1, L2 M2 N2 is equal to. So this is what is going to be the equation of plane passing through these two lines if they are coplanar. So that is what is the next. Now suppose we have been given a point and we have been given a line, then what are the coordinates of a foot of perpendicular and what is the distance of that point from that line? That is what we are supposed to find out now. Okay, so the line is given to be, the point P is A comma B comma C, and the equation of line is x minus x1 upon L, y minus y1 upon M, z minus z1 upon N. Suppose this is the line and this is the point. The line is there and the point is there, A comma B comma C, and we are supposed to find out, suppose this point is P, then this point is F. Okay, we are supposed to find out the coordinates of foot of perpendicular and the distance PM. That is the job given to us. What is the vector which is parallel to this line? Li plus Mj plus Nk. Okay, and what is any general point? What is any general point on this line? Let us say the parameter lambda now. So x is equal to x1 plus lambda L, y is equal to y1 plus lambda m plus comma z is equal to z1 plus lambda m. So any general point on the line in terms of lambda as a parameter, we can write it like that, and therefore let m be going to be this point, and now pm is going to be perpendicular to this. Therefore pm, what is pm? Vector pm will look like x coordinate of m minus a, so x1 plus lambda L minus A times I plus y1 plus lambda M minus B times J plus Z1 plus lambda N minus C times K is going to be vector PM, and now vector PM perpendicular to LMN should be 0, so that is what is going to give us the value of lambda. So x1 plus lambda L minus A times L plus y1 plus lambda M minus B times M plus z1 plus lambda N minus C times N should be equal to 0. Now if you observe and try to collect the lambda on one side, the lambda value we can directly say that x1 minus A times L with negative sign, so minus of x1 minus A times L plus y1 minus B times M plus z1 minus C times N, that is what is going to RHS, and in the denominator you have L plus M plus N. That is what is the value of lambda. If we substitute this value of lambda back into this equation, we get x coordinate of M, y coordinate of M and z coordinate of M. I am not writing it, but it is easy. And now the moment you get the x, y, z coordinates of M, you should be able to write down the distance M. Now it is going to be a big formula in terms of ABC, x1, y1, z1, L, M and N. Do we really need to remember that? We need not have to remember. If we understand how are we going to deal with it, every time you get a numerical problem, you are supposed to do anyway these calculations, and you will be able to find out the distance of any point from any line. Now there is distance between two skew lines is to be found out, and distance between parallel lines is to be found out, and distance of a point from a plane is to be found out. Now I will do distance of a point from plane right now in this video, and remaining two things which are remaining, which is distance between two skew lines and distance between two parallel lines, you can try on your own or refer to the notes. It is absolutely simple, and anyway we have done it in vector. So let us now do the distance of a point from a plane and put a perpendicular. Okay, so we have been given a plane ax plus by plus cz plus d is equal to 0. Suppose this is the equation of plane, and if there is a point P, x1, y1, z1. Okay, here one thing I would like to bring it to your notice. Again, this is going to be analogous to what we have done in two-dimensional geometry, where we have found out distance of a point from a line. If line is ax plus by plus c is equal to 0, and if point is x1, y1, then the distance we got was equal to absolute value of ax1 plus by1 plus c upon radical a square plus b square. That is what was the distance that we have got, and let us see what do we get over here. So what is the procedure? You drop perpendicular from P on this, let that point be M, and PM is going to be perpendicular to this plane. So what is the perpendicular vector? Anyway, we know perpendicular vector AI plus BJ plus CK is a perpendicular vector to this plane. Therefore, equation of PM is equal to R, which is equal to x1, or maybe let us write down equation of PM. Line PM is x minus x1 upon A, which is equal to y minus y1 upon B, which is equal to z minus z1 upon C. So any point is equal to lambda, which is x is equal to A lambda plus x1, y is equal to B lambda plus y1, and z is equal to C lambda plus z1. Any point on the line PM will look like this. Now M is a point on line PM as well as M is a point in this plane. Therefore M must satisfy this. If we substitute M back over here, what should happen? We should get value of lambda. For that value of lambda, the point on the line is also point on the plane. Therefore, if we put that equation back into the equation of plane, then we get A times A lambda plus x1 plus B times B lambda plus y1 plus C times C lambda plus z1 plus D is equal to 0. Now can we directly write down the value of lambda here? Lambda is going to be ax1 plus by1 plus cz1 plus d with opposite sign. So minus of ax1 plus by1 plus cz1 plus d, that is what is our numerator, which goes to RHS, and in the denominator we have a square plus b square plus c square. And therefore let me write down any point x is equal to x1 plus a lambda, and lambda is this, therefore minus a times ax1 plus by1 plus cz1 plus d divided by a square plus b square plus c square. This is your foot of perpendicular x. These are the coordinates of M that we are finding out. This is x coordinate, exactly similar will be y coordinate, exactly similar will be z coordinate. Now you will be surprised to see this formula also, that in two-dimensional geometry we had exactly same x1 minus a times ax1 plus by1 plus c upon a square plus b square. Now only one parameter is getting added because that geometry from 2D became 3D, otherwise this is exactly same. Now this you want, this is to be enjoyed, this is to be appreciated that it happens. And now finding out distance, so you find out y and z, and then finding out distance is not going to be a big deal. And if you simplify after that, the distance of a point, distance PM, would look exactly like ax1 plus by1 plus cz1 plus d divided by radical a square plus b square plus c square, which is exactly similar to the formula that we had developed for straight lines. So this is what is the equation, the formula for finding out the distance of a point from a plane. Now I will go through all lecture notes again. I will check what is missing, what we have not covered in lecture notes. Otherwise, by and large, 90%, 95% of the problems in Cengage you can solve with this much theory, which you should try. And if there is something missing, like I know I have to spend some time on three-dimensional geometry, proving some theorems. There are 22 theorems to be proved. If we can make lectures of that, we will do it. Then maybe I will have to explain you the volume of sphere, which takes care of y is the volume of cone 1/3 of that of cylinder, etc. So maybe that is also another thing which we require to do, which we will do. And then few lectures on tetrahedron and spheres, which we will do, but by and large you should be able to do maximum number of problems in your source on vector 3D based on these many lectures. Okay, so thank you. This is lecture number 15 which is done. See you in the next lecture. Thank you.